Hello, I am Young-Sik Yoon, a PhD student at PostTech. Today I will present a joint work with Jinan Nam, Hyo Jung-yoon, Jae-woo Lee, Dong-woo Kim, and Jung Soo-rok titled Few-Shot Learning. Machine learning is the task of excising a specific target dataset from a trained model. The goal of machine learning is to mitigate unwanted behaviors of the model that may have been induced by the target data, which are mislabeled or privacy sensitive. While retraining a model from scratch with using the data to be retained is a straightforward solution, we call it as an oracle model, but it is costly. To this end, previous learning methods aim to approximate such a oracle model by utilizing training data. They have demonstrated that such a learning can be successfully performed whenever a complete indication of the training data is given. However, it is often impossible to do so whenever the original training data is not fully accessible due to memory cost or privacy concerns. For example, we can consider online learning or federated learning scenarios that does not store data due to a shortage of storage space or privacy concern. Besides these recording limitations, the target data can be overwhelmingly many to be minutely specified in the training dataset. With the limited access to target samples, we call it as few-shot learning. The desired model behavior on inaccessible samples is prone to be ill-specified. For example, consider a classifier trained with a spoiled MNIST dataset where hundreds of crossed sevens are mislabeled as 2. Goal of learning in this example is correcting the label of the crossed 7. Given a target dataset consisting of only few images of crossed 7, the response to crossed 7 after a learning may still be 2. As retained dataset after excluding only the few target data still includes hundreds of the mislabeled crossed 7. Meanwhile, the learning requester might have different intentions beyond learning the few target data, such as a standard learning to exclude the influence of all the mislabeled crossed 7. However, even when all the samples of crossed 7 are identified and requested to be erased, the response of the retained model to the erased sample can be still ill-determined and possibly changing over training epochs. This demonstrates that just removing is insufficient and unstable. If we know that a mislabeled cross 7 actually should have been labeled as a 7, it would make sense to correct the label rather than simply removing it. In the intention for mislabel correction, we propose the intention of correcting the label of mislabeled cross 7s to the correct label 7, and incorporating this correction into the learning process. For privacy protection, we consider a membership inference attack, which involved determining if a data was used in training based on confidence. To enhance robustness against this type of attack, we propose an intention to maintain predictions of original model while decreasing confidence through the use of soft label. To address these challenges, we propose a 3-step framework consisting of model inversion for data accessibility, filtrations for identifying target-like data, and relearning with intention. We explain our framework step by step, and first step is model inversion. For the model inversion step, we design a new inversion technique specialized for learning that fully utilizes the knowledge at hand in the context of learning, the trained model, the target samples, and the general prior on the data domain. We propose 2 new losses for model inversion, target loss and augmentation loss. Target loss measures the semantic discrepancy by reversing a few-shot target data, and augmentation loss measures the robustness on augmentation. And the second step is filtration step. In the filtration step, first we filter out images where the quality generated by the generator is insufficient. To be specific, we use the original model to filter out samples with low confidence. Then, we differentiate between samples that are similar to the target dataset and those that are not. For this, We measure the distance in the embedding space between the given viewshot of the target data and the generated samples. And then our last step is rerunning step. In the rerunning step, we devise a set of rerunning strategies which relabels the augmented target dataset differently from the filtration step to impose a learner's intention accordingly for standard learning, protection from a membership inference attack, and mislabel correction. The goal of standard learning is removing the target-like data. For evaluation, we use accuracy on both the data to be erased and data to be retained. However, because of the ill determination of its intentions, it is not easy to prove that the model has truly unlearned the target data. For privacy attack protection, we do not remove the target-like data, just relabeling them. The goal of privacy attack protection is protecting the target-like data against membership inference attack. Ours defend and ours untrained relabel the target-like data with an output of an untrained model F untrained. Specifically, ours defend follows the weighted sum of the output of original model and untrained model, and ours untrained follows only the output of untrained model. In this scenario, we evaluate performance of unlearning by attack success rate. For mislabel correction, we also do not remove the target-like data and relabeling them. The goal of mislabel correction is correcting label of the mislabeled target-like data. We propose two intentions, correct and negative. Ours correct relabels the target-like data with the true label when we already know the true label. Ours negative is for the situation where we do not know the true label. We just adjust loss into a negative loss for mislabeled label. We evaluate the unlearning performance by accuracy on the unlearned model. We demonstrate our method on three scenarios, which are class removal, privacy protection, and mislabel correction. In class removal scenario, we remove all data belonging to a class. In privacy protection scenario, we aim to make Crossed7 safe against membership inference attack. We report both test accuracy and attack success rate of a learned model for this scenario. And in mislabel correction scenario, we use a spoiled MNIST dataset, which all of Crossed7s in MNIST is mislabeled as 2. And the goal of this scenario is that correcting mislabeled Crossed7s to correct label 7. In every scenario, we report the performance of our method for when all target data is available and when only 3% of the target data is provided. And we compare with Oracle with each intentions and existing unlearning methods with almost full access to the training and target dataset. It is clear that in class removal scenario, the ideal behavior after standard unlearning is just to give zero predicted probability to class 7 for any input, while accurately classifying samples in the other classes. In table, both our method with standard and untrained intentions consistently demonstrate near zero accuracy for data to be erased, regardless of the quantity, while they maintain high accuracy for data to be retained, even though data to be retained is not provided. This indicates that the proposed model inversion method can generate suitable images for preventing catastrophic forgetting. In privacy protection scenario, we evaluate unlearning methods using a measure of privacy leakage, which is attack success rate of a membership inference attack method. If unlearning to defend this privacy attack is successful, then the attack success rate of the data to be erased would be low, while the model accuracy is maintained. We observe that privacy-oriented unlearning methods, ours untrained and ours defend, exhibit significantly lower attack success rates on data to be erased than ours standard, while keep the accuracies on both data to be erased and retained. A plausible intention in mislabel correction scenario is correcting the mislabels on Crossed7. Therefore, an ideal unlearning would be correct oracle of high accuracies on both data to be retained and data to be erased. In the table, we observe a substantial gap between ours correct and ours standard. This gap implies that more than just erasing is necessary to remedy the misbehavior induced by data to be erased. To sum up, first we established the few-shot unlearning problem that embraces not only the standard unlearning but also the various explicit intentions such as privacy attack protection and mislabel correction. Second, we devised the unlearning framework consisting of the model inversion, filtration, and rerunning, each of which is tailored to address the few-shot unlearning problem with useful intention. Thank you for listening.